Hello, and welcome back to Compressible Flow. I'm Steve Miller. Today we'll be talking about a new module of Transonics. Today in particular, we'll talk about transonic flow definitions. We'll discuss what is a transonic flow. Part of understanding transonic flow is understanding its historical context, and therefore today's class will have a particular attention paid to the historical developments of transonic flow. We'll look at the three major historic developments, which of course hold true today because they're physics, and physics doesn't change, of transonic flow with respect to its theory. And therefore we can understand the physics of transonic flow, which is one of the most perplexing and difficult areas of contemporary aerodynamics. Let's get started. Let's start with a fun quote from none other than Dr. Theodor von Karman in his Cornell lecture in 1953. And we'll read this together. Dr. Karman wrote and lectured, "We call the speed range just below and just above the sonic speed Mach number equal to 1. The transonic range. Dr. Hugh Dryden and I invented the word transonic. We had found that a word was needed to denote the critical speed range of which we were talking. We could not agree whether it should be written with ones or two S's. Dryden was logical and wanted two S's. I thought it wasn't necessary and always wanted to be logical in aeronautics, so I wrote it with one S. I introduced the term in this form in a report to the Air Force. I am not sure whether the general who read it knew what it meant, but his answer contained the word, so it seemed to be officially accepted. I will remember this period, 1941, when designers were rather frantic because of the unexpected difficulties of transonic flight. They thought the troubles indicated a failure in aerodynamic theory. Indeed, this is where the origin of transonics came from, in a letter to the United States Air Force and its response. And indeed, the argument, perhaps, between Dryden and Karman was resolved by the acceptance in the community of the new word, which they coined, transonics. Perhaps it means the transition between subsonic and supersonic flows. And this is very important in the time period, of course, because the advent of supersonic flight and trying to break the so-called sound barrier to go faster than the speed of sound with a vehicle. Now let's look at some particular notes of transonics. Indeed, transonics might be characterized a few different ways. First, it could be characterized by the so-called drag divergence phenomena. This is where a rapid shift of center of pressure, an unsteady and somewhat unpredictable effect of shock waves on control surfaces occurs. Indeed, in this class, you'll have seen back in the very beginning, we were showing many different Schlieren images of transonic flow and how normal shock waves move around the surface quickly in this transonic regime, making aerodynamic phenomena very difficult to examine and understand. In this class, we'll also look at the so-called drag divergence phenomena, where the drag rises like a barrier as the vehicle moves towards the speed of sound. Indeed, even today, most commercial airliners fly in the range of Mach 0.7 to 0.88, which is indeed the transonic range, because of course there's normal shocks forming on the vehicle, and we've shown previous pictures of this in this class. Now, we might want to push the so-called Mach numbers closer to unity, but that will require a greater understanding of transonic drag. Perhaps today we are still deriving and showing and creating test vehicles that operate in the true transonic range, closer to Mach 1, rather than, of course, the low transonic speed range, say Mach 0.75 to 0.88. Here's one perhaps conceptual artwork photo of what might be a transonic aircraft. This is a conceptual photo from the Boeing company. You can see it has canards and very interesting integrated engines with the wings. This whole vehicle is designed to have low drag and fly near Mach 1. The advantage of this type of vehicle is, of course, you can go a little bit faster without much more fuel gain, or loss in this case, as the aircraft might be a little bit faster than contemporary commercial tube and wing aircrafts today. It has a unique design. Let's consider more about transonic flow. So this Boeing aircraft is a so-called sonic cruiser in that it departs from classical tube and wing configurations. You'll notice the engine placement, wing placement, etc., and the integrated engines on the wing. Now, if we go back to the 1940s, you'll see that there indeed was a serious lack of aerodynamic data in the literature and wind tunnels and theory in the transonic range. That's because there's very large changes of all aerodynamic variables near the transonic condition, which change rapidly, and they cause extreme difficulty in the particular measurements. In fact, measuring transonic flow is very difficult because of all the normal shock waves that appear in the tunnels. According to subsonic and supersonic linear theory of pressure coefficients and their corrections for slender bodies, we might find a pressure coefficient in 663 of this slide deck and 664 of this slide deck equations of Cp divided by the square root of 1 minus Mach number and Mach number squared minus 1 respectively. Of course, the Mach numbers just switch so that we have a real value and don't have an imaginary value, e.g. square root of -1 in the denominator. This might be viewed as an off-design parameter, away from, say, the transonic condition. As m infinity approaches 1 from above or below the transonic point, we of course find particular singularity, and C sub p blows up according to slender theory. So this theory isn't very useful. You can see that, indeed, as the denominator approaches 0, the Mach number approaches unity, and this extremes impossible large values for Cp. But indeed, we do see large value increases of C sub p on actual measurements. This is, of course, part of the idea of the rise of the drag as we approach the so-called sound barrier. Thus, you can see the transonic regime is extremely sensitive to Mach number. We can indeed today use the invention of slotted throat wind tunnels, that is, where a test section has holes in it, to help alleviate the transonic measurements. If our wind tunnel test section has holes or slots in it, then this helps reduce the reflection of shock waves in the transonic flow. This is obviously very advantageous. Today, CFD has helped tremendously in predicting transonic flows. It's an essential tool because it's so hard to do the work analytically or experimentally. Also, transonic flow is a challenge to modern engineers even today in the contemporary era, who examine both commercial flight and, of course, contemporary fighter aircraft that operate at low and high transonic speeds. Why might this be? Also, transonic flow is important for space applications during ascent and descent, which, of course, all vehicles go through as they go to orbit. So for those interested in space, transonics is an essential subject. Let's make some basic observations of transonic flow. First, let's make a definition. We'll introduce the critical Mach number, m sub cr. The critical Mach number is the free stream Mach number at which sonic flow is first obtained in a body. Therefore, m equals some subsonic value where transonic flow is first obtained. Thus, in the transonic regime, we could be viewing as when, with MCR, the critical Mach number is indeed reached. Transonic flow is a mix of regions of locally subsonic, supersonic, and of course transonic flow in both space and time around the flight vehicle or anywhere in the fluid that we're examining. We'll examine particular transonic flow as an example over a flow of the so-called NACA 64A006 airfoil. The 006 means it's 6% thick. It's not like James Bond. We'll note the various shockwave patterns as well as the regions of the flow separation over the NACA 64A006 airfoil. We'll superimpose particular pressure coefficient distributions over the top of the surfaces so we can understand it better. And we'll examine the so-called supersonic pocket of flow, which consists of weak expansion waves, which of course terminate at a sonic line where the flow becomes supersonic again. This is often observed and of course near the normal shocks attached on wings in supersonic and transonic vehicles. We'll also note separations and boundary layers due to the attack shock, which makes transonic flow even more difficult. Let's look at one particular series of Schlieren of this particular airfoil. This shows Schlieren photographs in figure 4.1 of the slide deck of increasing free stream Mach number for transonic flow. Here's each of these Schlieren images, which is of course 12. And we look at NACA 64A006, 9, and 12. So this column has a 6% thickness, 9% thickness, and the third column has a 12% thickness respectively. The top row is Mach 1, incoming Mach 1, Mach 0.94, the third row is Mach 0.87, and Mach 0.79. We have superimposed a little coefficient of pressure as the white line on all these figures from the original NACA report. Take a few minutes and see how coefficient of pressure changes with the flight Mach number and thickness. What trends do you see? Let's make some observations about the previous figure. First, you can see that the flow is caused and its separation by a shock wave boundary layer interaction, where of course the shock wave, a normal shock wave on the wing, interacts with the turbulence and it creates a separation. That is, the flow separates from the airfoil and recirculation occurs on the airfoil, which is of course not very good for lift. The pressure will increase across the shock wave, which we have learned previously, and it represents a very strong adverse pressure gradient, which of course helps cause flow separation. We indeed know that the regular turbulent boundary layers, which we previously looked at in this class, when a surface has an adverse pressure gradient, might separate. When a shock wave is near the surface, the boundary layer occurs and encounters an adverse pressure gradient and will almost always separate because of the normal shock interaction. The shock boundary layer interactions always cause very large rises in drag, and this could be called the drag divergence phenomena, which is always associated with the transonic flow. We'll examine a particular figure of now the drag divergence phenomena where the curves correspond to different angles of attachment. Let's do that now. Here in figure 402, we're showing the variation in the drag coefficient with Mach number for an NACA 2315 airfoil. The drag diverges as Mach approaches unity. The experimental ranges from an angle of attack on the airfoil from -1 to 5 degrees alpha. Here, the x-axis is Mach number, and the y-axis is the coefficient of drag on the airfoil. Each line corresponds to a particular angle of attack, from -1 to 5 from top to bottom. You can see as Mach number goes from 0.4 to say 0.7, 0.8, almost all the CDs align up almost and collapse on the same line, which is obviously fascinating. You can see in this particular case that as the Mach number increases, the coefficient of drag rises like a barrier. In fact, the curve never even approaches Mach 1 on the graph and figure. And therefore, this is partly where the idea of the sound barrier came from, because as the flight vehicle approaches the speed of sound, Mach 1, the drag rises like a barrier. Therefore, the sound barrier is really referring to, in its slang, as the drag coefficient rise as we try and approach the transonic condition of Mach 1. Now let's try and perform some particular analysis of this flow. We'll do this through the Euler equations. This is an inviscid theory which consists basically of the Navier-Stokes equations with, of course, the viscosity set to 0. We'll assume that the flow is inviscid, it's adiabatic, and indeed there are no body forces. We'll also assume that the flow has a large entropy losses and that the flow is rotational according to Krokos' theorem, which we haven't reviewed in this class, but you'll have to take my word for it for now, or you can look it up online. The first equation, of course, is conservation of mass, the second, momentum, and the third is an energy equation written in terms of total enthalpy. Let's look at this particular flow and analysis. Indeed, we also must account for entropy changes across the shock. We previously developed this relation. Also recall that Cp equals gamma r over gamma minus 1, which you learned from traditional thermodynamics theory. Then, of course, the entropy across the shock wave might be written as equation 668 in terms of Mach number because we know the pressure and temperature relations across the shock. This entropy rise across the shock might be written as delta S, which is the entropy change divided by the gas constant, goes as two logarithms, natural logarithms that is, with respect to Mach number and gamma, where m1 is the Mach number in front of a normal shock. We'll make a substitution. We'll let little m equals m1 squared minus 1. And the term in the second brackets will be equal to, upon substitution in 668, of 1 over m plus 1 times the quantity gamma minus 1 over gamma plus 1, m plus 1. Now for transonic flows, we know that m1 is approximately 1, and therefore m is much less than 1. Therefore each log term is of the form 1 plus epsilon, where epsilon is much less than 1. Of course, because m1 is just above 1. 1 plus epsilon. We performed a similar asymptotic analysis when we studied normal shock waves, and we're really doing the same thing here. We can also note that our new form, that the logarithm of 1 plus epsilon will go as epsilon minus epsilon squared over 2 plus epsilon cubed divided by 3 plus higher order terms. Of course, epsilon is very, very small, so we should expect that log of 1 plus epsilon will go as epsilon. Using these definitions, we can simplify our entire equation 668 of the slide deck into 669 of the slide deck. And we'll have a delta S the entropy after and before the shock, the difference, divided by the gas constant will go as 2 gamma all over 3 gamma plus 1 squared times m1 squared minus 1 cubed. Indeed, this will show that the entropy increases across a shock and will be of the third order of m1 squared minus 1, indicated by this cube. This is an obvious analysis. Then, of course, m1 squared minus 1 will be much, much less than 1 because, of course, m1 is approximately just above 1, according to our assumed analysis of 1 plus epsilon. Therefore, you can see upon substitution that the entropy increases across the normal shocks attached to a transonic flow of a slender body are very, very small, and so there's very little entropy gain. The strengths of the shocks will then be given by our previous analysis of delta P over P. That's the pressure rise across the shock divided by the static pressure in front of the shock, and therefore it's a net proportional to m1 squared minus 1. You can see this from, of course, the pressure rise equation with Mach number for standing normal shocks. We can then infer and deduce that the entropy rise is approximately third order with shock strength. So indeed, both the entropy rise and change in pressure across the shock goes as third order of the shock strength. We'll assume that the flow is nearly isentropic everywhere, except, of course, these shocks, but it's such a small entropy change across the shocks, we'll just neglect it, of course, because it's a transonic flow. We can then, in turn, from this analysis, assume that the flow is essentially irrotational. Not truly irrotational, but essentially. With the Euler equations and this analysis, we can then infer that the velocity potential compressible Euler equations can be written in the form of 670. This is a very important equation. Let's look at it. Phi, capital Phi, is of course the velocity potential, which we can use to recover the velocities of the flow. Here c is the local speed of sound. The sub yy, sub xx, sub zz, and mixed derivatives are all partial derivatives acting on phi in the first and second order and mixed derivatives respectively. So this equation, with our assumptions, should hold for any body, thick or thin, at any particular angle of attack, as long as our assumptions hold true. Of course, this is theoretical and it does not account for the turbulent flow, which is important. Now, if we assume that the perturbations of the velocity potential are small, then we can find the so-called perturbation velocity potential equation. Performing a small perturbation analysis will yield the following equation 671 from equation 670. You'll see this here, that we allow only small phi to be written as a function of, say, capital Phi bar plus phi. So therefore, our total velocity potential can be written as an average plus a perturbation. Therefore, we have two equations. This equation holds for the perturbation velocity in 3 dimensions. And so we're only looking about perturbations about the incoming flow capital Phi bar, which is, of course, ambient relative to the vehicle. This is the so-called transonic small perturbation equation, which is a celebrated equation in the transonics field in the theory. We'll non-dimensionalize this equation using a particular parameter tau, and we'll write tau as b over c. B will be defined and c will be defined as the maximum thickness and length scales of the body respectively. So here, c is not the speed of sound, it might be viewed as the chord. B, of course, is the maximum thickness, as shown in figure 403 at the bottom of the page. Here, tau equals b over c. Simple. Now, we'll assume that tau is small. Therefore, all our transonic bodies will be, of course, slender. We'll transform our coordinates as x over c, y as y tau to the third over c, which is dimensionally correct, and z bar as z tau to the 1/3 over c. X, y, and z are our spatial coordinates, and we non-dimensionalize them with respect to the chord or length scale of the vehicle, and of course, its thickness ratio, or so-called slenderness ratio, tau, which goes into the y and z transform. We choose these carefully, and now we're able to define a non-dimensional perturbation velocity potential according to dimensional analysis, and we find a non-dimensional perturbation velocity in 672. We can write that as phi over cu infinity tau to the 2/3, as shown in equation 672. And therefore, we have a non-dimensional perturbation velocity potential equation for slender transonic bodies. We can substitute our dimensionless forms of x, y, z, and tau, and non-dimensional phi into the equation for the slender perturbation. And we find, after combining these terms, equation 673. Here we have 1 minus m infinity squared over tau to the 2/3, minus m infinity squared times gamma plus 1 phi bar sub x, which is partial phi partial x, all times phi bar sub xx bar plus phi bar sub yy bar plus phi bar sub zz bar. Here, for example, this term, first phi bar term, is the partial derivative of phi bar with respect to x bar. So these are non-dimensionalized partial derivatives. These are the second order partial derivatives in the x, y, and z directions respectively. It's all equal to 0. It should remind you very much of the Laplace equation with the first coefficient being non-zero. M sub infinity is the global Mach number, which we reviewed in the beginning of this class. That's the Mach number, say, of the vehicle traveling through the atmosphere. And tau, of course, is the slenderness ratio, which is only dependent on the vehicle itself. So you'll see and look at equation 673, and what do you see if you perform this analysis for the first time? Indeed, you see this first parameter here. We'll call that 1 minus infinity squared over tau to the 2/3 k, capital K. And this is what we defined in transonic theory as the transonic similarity parameter. It's a non-dimensional number, just like, say, Reynolds number or Prandtl number or Rayleigh number or any of the other multitude of non-dimensional numbers that are important in aerodynamic theory. The transonic similarity theory parameter is K. Now, we can assume that the Mach numbers are near unity, which we already did, and substitute this in, and we can write, therefore, a more compact form of 673 with the transonic similarity parameter K. We'll write that as 675, K minus gamma plus 1 times partial phi bar partial x bar plus partial phi bar partial y bar plus partial phi bar partial z bar. And it's all equal to 0. 675 is the famous transonic similarity equation. This equation shows that for two different flows, but with the same transonic similarity K, shown in 674, but even with different values of tau, then the solution of both flows in terms of phi bar will be exactly the same. This means that we can perform a wind tunnel test, and if we match K in the wind tunnel test with the flight vehicle similarity parameter K in flight, then we can find the same values of phi bar, which we can then not dimensionalize into, of course, the actual velocities around the vehicle and lift and drag. It's all normalized by transonic similarity parameter. So the most important parameter to match between a transonic flow in a wind tunnel and the flight vehicle in the actual atmosphere is K. And we derive this from similarity theory. And indeed, this is what has driven transonic wind tunnel tests for actual flight vehicle testing for decades and was a major discovery. Without this discovery, I think we would not have made this particular flight vehicle successful. We can then, of course, find the most important parameter, which is the coefficient of pressure. The coefficient of pressure, Cp, can be divided by the slenderness ratio to 2/3, and that will go as negative 2 partial phi bar partial x bar, which is only a function of K, x bar, y bar, and z bar. So there's three major ways of examining transonic inviscid flow theory. The first is through the Euler equations, or Navier-Stokes equations, through CFD. The second is the solution of the potential equations, which gives approximate weak solutions of the normal shocks, which we showed in this class. And finally, the solution of the small perturbation equation, which will give further approximations for thin bodies at small angles. And this is where, of course, we found the transonic similarity principle through the dimensional number K. We'll note that all these equations are nonlinear, and this means the nonlinear nature of the equations is what leads to the traditional linearized aerodynamic theory to fail, which you learned in your undergraduate and previous classes in traditional aerodynamics. This is why the simple potential flow theories do not work, because they're linear, and you can see the equations which govern transonic flow are nonlinear, which rise and give the barrier, the so-called sound or drag barrier, which we saw in traditional media. Indeed, we must solve all these equations with numerical methods, but it does give our experimentalists a wonderful tool of knowing about the hypersonic similarity parameter. Let's look at some particular historic viewpoints of transonic flow. You'll see that Chuck Yeager was the first pilot of the XS-1, which obtained a Mach number of 1.06 in his first flight. This was indeed the first aircraft to break the so-called speed barrier and fly faster than the speed of sound at sea level. Indeed, there were earlier aircraft that broke the sound barrier and, of course, transonic dives, especially in World War II. Unfortunately, these aircraft often broke up in flight because they didn't have the structural rigidity and strength to survive the transonic regime and its huge rise in drag. The success of the Bell XS-1 was indeed followed by 30 years of intense research in transonic flight from the 1950s, and it's still happening today. In fact, Leonardo da Vinci and Galileo themselves postulated that the drag of the vehicle goes as the first power of velocity. This was wrong, and you can see this in their early notebooks, which are published online. Check them out for yourself. Indeed, down here in figure 404, Chuck Yeager was sitting in the cockpit of the Bell XS-1 for a media photo shoot after the first flight. Let's look at some other historical viewpoints of transonic flow. Edmé Mariotte and Christian Huygens, both French Academy of Sciences, founded the velocity square law, which worked well for low subsonic speeds. And you indeed found this velocity square law in your previous classes. It talks about how the drag goes as the square of the velocity. This works for low-speed flow, but obviously not for high-speed transonic flow. That's not very exciting. Benjamin Robbins was indeed a mathematician and a ballistician. He examined the first transonic aerodynamic effects and wrote that, and I quote, "The velocity at which the moving body shifts resistance is nearly the same with which sound is propagated through the air." Later in Germany, in the journal Artistische Mannschaft, Bensberg and Crane showed that the graph of CD, the coefficient of drag, versus U in the range of 300 to 400 meters per second. Recall at sea level, indeed, the speed of sound is about 340 meters per second. Therefore, they were plotting CD for particular artillery shells for 50 caliber machine gun bullets in this speed range. So the early aerodynamic tests were actually on machine gun bullets of 50 caliber. And this is why if you look at the front end of the Bell XS-1, it looks very much like a 50 caliber bullet. Take a second and look at the fuselage on the right in the nose. Indeed, that has almost the exact same contour shape as a 50 caliber bullet. And this is based on the early German studies. This, of course, helps find the first curve of transonic drag rise in their famous graph of CD versus U. They showed that the drag actually decreases after Mach 1, which is absolutely significant and strange. And so there's a huge drag around Mach 1, which was shown through the traditional CD equations that are normalized, of course, with the square root of m infinity squared minus 1 in the denominator. Later, in the United States, at the Army Engineering Division, McCook Field near Dayton, Ohio, two people named Caldwell and Falls, now the Air Force Research Lab at Wright-Patterson Air Force Base, conducted a series of experiments on airfoils for the purpose of studying propeller blades. And these, of course, were residing in the transonic regime. They conducted the first wind tunnel tests involving high-speed flow over stationary airfoils. And they show how large drag increases in lift near, of course, the transonic range, and then decreases lift tremendously in the transonic range. This means that there's a total loss of lift as, of course, we approach the sound barrier of the vehicle, which causes it, of course, to fall out of the sky. And we needed better designs to overcome the transonic regime. They indeed further measured the compressibility effects on an airfoil, which they called the critical speed. Not soon after, Hugh Dryden, and of course Dryden Research Center in California of NASA and NACA was named after him at Dryden Field today. Today it's renamed Armstrong Research Center. And his collaborators performed experiments published in the NACA called Report Number 207, which you can see for yourself on NASA Technical Report Server. Go ahead and download it and check it out. Dryden wrote, "We may suppose that the speed of sound represents an upper limit beyond which an additional loss of energy takes place." This is probably due to the shock waves. "If at any point along the wing the velocity of sound is reached, the drag will increase. Therefore, from our knowledge of the flow around airfoils at ordinary speeds, we know that the velocities near the surface are much higher than the general stream velocity, the increase being greater for larger angles and thicker sections. This will correspond very well with the earlier flow breakdowns for thicker wings and all the wings at higher angle of attack." End quote. Thanks, Dr. Dryden, for that insight. And that was a huge and amazing report at the time, which shook the transonic world. In the 1920s, the NACA of the United States started a major research program, the Transonics. Briggs and Dryden at what is now Dryden Research Center, built new, smaller, high-speed wind tunnels with only 2-inch diameter jets. The Mach numbers of these jets was 1.08 and allowed them to understand transonic aerodynamics. They inserted a number of airfoils in their early work and executed the first supersonic wind tunnel experiments in the United States. And they showed 3 major findings. The first was that the flow separated from the upper surface, but it did not show that it was due to the shockwave boundary layer interactions. So they saw the flow separations but didn't understand why the shockwave separated the boundary layer. They showed that the drag coefficient for the airfoils in their transonic wind tunnels followed the same type of drag divergence encountered for projectiles from the German experience many years earlier. And they found, of course, this drag coefficient divergence between Mach number 0.95 and 1.08. After 1.08, of course, things settled down again and they had lower drag and, of course, recovery of lift. They observed for the first time ever the bow shock standing in front of the leading edge of the airfoils, which is very much unlike the Mach experiments of the bullets. Here they connected the idea of course, wind tunnel experiments in the transonic regime of airfoils with the early supersonic bullets of the Mach experiments, which we discussed earlier in the class. Indeed, their work led to researchers such as Eastman Jacobs, John Stack, and most importantly, theoretician Theodor von Theodorsen to produce major breakthroughs and the first widely viewed transonic Schleiermacher image. Let's talk about the historic figure Theodor Theodorsen, who worked at NASA Langley Research Center, which still exists today. Indeed, he was Norwegian, and he was an American immigrant. This is his photo on the right. He was born in Norway, and he received his doctorate at Johns Hopkins Universities. Then, he was a theoretician at Langley. He is known for a number of things as the first noise researcher, one of the first noise researchers at NACA and NASA. And he worked in a number of fields like bomb detection, wind tunnel development, air elasticity, turbulence, and indeed he became the chief scientist of the U.S. Air Force from 1950 to 54. Personally, he was married, and of course, in 1922 before coming to the United States, and they had a few children. He is a really smart person who worked in turbulent theory, though it's not well adapted today. But many other areas, like air elasticity, actually captured his name. For example, the Theodorsen function is a famous function in theoretical air elasticity. Let's look at a few more historical viewpoints. Here's figure 405. This is a wind tunnel model of the Bell XS-1 at NASA Langley Research Center in 1947. This is, of course, the model of the first supersonic aircraft, which broke the sound barrier. Now, these early models were inserted in the transonic flows, which choked the tunnels, and research, of course, was unable to be conducted. Recall our discussion of supersonic wind tunnels. The cross-sectional area of the test section is smaller when you insert a model, and therefore it rechokes the flow, and studies are therefore impossible to conduct, especially at transonic speeds. How could this be overcome without changing the tunnel? It can't. And so we actually altered the tunnel and not the model to try and find supersonic and transonic experiments of these vehicles. Here's a more contemporary picture of a transonic test section. This is a slotted test section of the Florida State University Polysonic Wind Tunnel. I took this picture in 2018 with my cell phone camera, which you can actually see in the glare of the tunnel. But you can see there's these long slots. So we're looking down the test section, which is removed from the tunnel, seen in the background. Basically, these slots reduce the reflections of the shockwaves in the tunnel and overcome the area changes which occur when we block the tunnel with a particular small device. These slotted tunnels and perhaps perforated tunnel walls were a key development in the United States and were a Cold War secret for many decades, kept from the Soviet Union. Now, in 1946, a fellow named Ray Wright, a theoretician at the NACA Langley Research Center in Hampton, Virginia, argued that a test section with long, thick rectangular slots parallel to the flow with an approximate 12% open area would reduce the blockage problem for transonic flows without any negative effects. He was essentially saying to drill holes in the side of their precious, world-renowned wind tunnels. A fellow named John Stack, who is the administrator of NASA Langley, approved slotting the 16-foot high-speed wind tunnel of Langley based on a simple paper by the junior engineer Ray Wright. This must have been horrible to many of the senior administrators and senior personnel because, of course, you were going into a wind tunnel and essentially drilling holes in the side of it. It was a ludicrous idea at the time, but it was backed up by the theory and mathematics of Ray Wright. This is a wonderful example of the power of theoreticians. Indeed, the slotting throat concept, used today in all transonic wind tunnels, helps smooth the transition in the tunnel through Mach 1 and remove the problem of blockage, therefore allowing the first functional transonic wind tunnels to be used for testing for transonic and supersonic flow in NASA Langley Research Center. This remained a state secret for decades. Indeed, there was no theoretical, analytical, or numerical method useful for transonic calculations until the 1980s, when CFD methods from those of, say, Mermin and Cole came to use. We will talk about these particular CFD calculations of Mermin and Cole in our next lecture on transonic flow. Today, we introduce the concepts of transonic flow, their theory and discussions on historical concepts, and derive the all-important transonic similarity parameter found from our analysis. It's important to remember this parameter and understand how it can be used to scale wind tunnel tests to flight vehicles for the flight range. We also looked at some history to, of course, solidify the concepts. Thank you very much for your time today. I'm Professor Steve Miller.